So I'm going to assume that all of the viewers of this video will have some acquaintance with object-oriented programming, or what is meant by object-oriented programming, and preferably you've been programming in a computer language using objects. First, a word about what is going to be covered and what is not going to be covered in this video. This video will take a closer look at the concept of a software object, and in particular how the software object is visualized in an application, or what objects can represent in a software application. What will not be discussed is how to develop applications using objects. Let's take a closer look at where and how the software construct called object came about and why it has become so important in software programming. I'm going to start with the definition of an object, but before doing that, I just want to make it clear that when you have a definition of something, that's not necessarily telling you how to use that thing. For example, if someone gives you an automatic coffee maker, the definition might be a device for automatically brewing coffee, but you're probably going to need the directions that came with the coffee maker to learn how to use it. And so the same thing applies to the concept of objects. The definition is necessary, but it's just not going to tell us how to use them in an application. So here's the generally accepted definition of an object. An object is a software construct which is composed of data in the form of variables and functionality that operates on that data. The concept of object includes these properties: encapsulation, identity, and polymorphism, and inheritance. Here is the definition of an object and its properties that will apply to this Visualizing Objects videos series. An object in object-oriented programming: a software entity that contains functionality in the form of methods. An object usually contains data which its methods operate on. Message: one object requests the services or functionality of another object by sending a message to that object. A message is a request for the receiver of the message to execute one of its methods and return the result of that execution. Encapsulation: restricting of direct access to an object's methods or data except as allowed through the object's interface. Identity: a unique reference to a particular object, usually an address in computer memory. The identity of an object can be used to find the object's type or class. Polymorphism: the ability of objects which are a subtype of the same parent type to respond to inherited functions with different behavior. And finally, inheritance. In object-oriented languages which implement class definitions, the subclasses of a parent class inherit the data and functions of the parent. Subclasses may redefine the behavior of inherited functions. A good place to start with any important subject is history. So how and why did the concept of objects come about, and how has that concept become so important in software programming? To see this, we need to take a brief glance at the history of computer programming. The first modern computers were created in the 1940s. They had limited memory and computational power and were programmed in the binary code of the computer. As the usefulness of the computer for solving problems in areas such as science and engineering became apparent, high-level languages were created to facilitate the writing of computer programs. Fortran was one of these early languages. It was procedural and implemented the concept of subroutines, which we now call functions. With the invention of the transistor, computers became more powerful. Programs became larger and larger, and then in the 60s, complexity of the programs written for the computer became a concern. Here's a diagram indicating how the complexity of computer programs was increasing as the power of the computer increased. Complexity in a computer program adversely affects the time of development and the application's maintainability. An application's maintainability refers to requests for modification and/or extensions to the application's functionality. This diagram shows complexity occurring in a procedural application. Here, the main section of the application and its three subroutines access the same data of the application. Changes of any subroutine code may require modifying some or all of the code in other parts of the application. Let's look at the language timeline again. We have seen that in the 1960s, the complexity of programs written for computers was becoming a concern. In 1962, the first computer language to use objects, Simula, was created to model real-world discrete event-driven processes on a computer in order to find optimizations for those processes. About that same time, computers are being networked together to solve larger problems. Then, in 1967, Alan Kay, a student at the University of Utah, imagines the concept of an application as a collection of little computers communicating. Kay's little computer was something he called object. Here we see the similarities between an object and a computer. Just as a computer has data and functions, an object has data and functions. Both a computer and an object have an interface through which a user may interact with them. The computer's interface is its keyboard and monitor. An object's interface is the collection of methods it exposes through its encapsulation layer. In both cases, the user, whether human or another object, may make requests and receive responses through the interface. It's interesting to look at Kay's concept that applications could be composed of little computers. These little computers were what he called objects. Here is an illustration of an application composed of objects. The application is shown within the blue circle. The objects of the application are shown as yellow circles within the blue circle. The objects are communicating through message passing to implement the overall functional requirements of the application. Each object may be visualized as a little computer implementing some cohesive chunk of the functional requirements of the application. Here we see how objects are good at managing complexity. An object encapsulates data and the functionality that acts on that data. The object's functionality is a small part of an application's overall functionality. In some sense, an object is a small computer application, and on our complexity curve, it can be represented as lying within the circle shown in red. And finally, we see that objects manage complexity by, one, encapsulating data with the functionality that acts on that data, and two, decomposing the functionality of the application into manageable chunks within each object.